2, 1. All right, here we go. Welcome to another exciting previously recorded lecture. Potentially the last one of the semester, hopefully. Anyway, so as per the announcement, Charlotte's not feeling well, so she's home. She is sleeping right now, so perfect time to get this recorded. So let's do it. All right. So let's recall what we were talking about yesterday in class and set up what we're going to be talking about today. All right. So recall that a matrix is said to be diagonal if the entries off of the diagonal are equal to 0. Right. So basically, right, the diagonal matrices are what you would envision. They're a matrix where the only entries of interest are hanging out on the diagonal. Now, again, it's worth stressing the diagonal entries can equal 0, that is okay, but the requirement is that anything off the diagonal must equal 0. So there's no requirement of what's on the diagonal, so the D11, D22, D33, so on and so forth, those entries, they can be whatever you want. There's no requirement on those. And, of course, we already ran into diagonal matrices when we were talking about matrix multiplication. That was a fun little practice problem that we had. The product of two diagonal matrices remains diagonal. And in class, we proved some things about how diagonal matrices work with multiplication. All right, so the other thing we proved in the class that's worth noting is that the eigenvalues of a diagonal entry are precisely the entries on the diagonal. Right, and we didn't fully prove it. We kind of just drew the picture and went, well, obviously, when you take the determinant, this is what happens. But it's not too hard to show. All right, so keep that in mind. Very important fact. Right. The other important thing we brought in yesterday in class was the notion of a similar of matrices being similar, which is again another way of for us connecting matrices via matrix multiplication. Right, so of course matrices being row equivalent meant that I could get from one matrix to another by row operations, which we noted involve matrix multiplication. And similarity also involves matrix multiplication, but instead of just multiplying on the left, there is also a right multiplication as well. All right, quite interesting. Now, as I noted, the significance of this particular algebraic expression will become much more apparent to you when you take Math 301, Abstract Algebra. Maybe you're taking that next semester, maybe you're taking it next year. But this sort of maneuver is quite frequent and is quite powerful. And for us, what we're currently discussing, the big fact about similar matrices is that they have the same characteristic polynomial, and thus they have the same eigenvalues. So we introduced and dissected both of these terms in class yesterday, and so the natural thing to do is combine these two ideas. So a matrix is said to be diagonalizable if you're similar to a diagonal one. Hence the name, just combine the two, similar to a diagonal. Now, why would you care about this? So, as we noted, there's a lot of deeper things going on here, especially with the notion of similar matrices. But there's sort of a clear surface value care that you would have of this. A diagonal matrix is real easy to determine the eigenvalues of. You just look at the entries on the diagonal. Similar matrices have the same eigenvalues. So if I have a matrix and I have a diagonal matrix, and I happen to know that they're similar, I immediately know the eigenvalues for A. So rather than going for the whole process of finding the characteristic polynomial and finding the roots of the whatever polynomial that is, if I already had in hand that A was similar to a diagonal one, I have just a super easy way of computing eigenvalues. Just read off the entries on the diagonal. Right, so surface level, there is power to being diagonalizable. It's easy to communicate the eigenvalues. But we motivated the discussion of this with an example of a matrix where the eigenvectors formed a basis. And it turns out, as we concluded the statement with yesterday, that diagonalization is precisely when that's possible. So a matrix is similar to a diagonal one if and only if its eigenvectors form a basis for Rn. And again, surface level, we're not going to get super deep into this. You might go, well, why would you care about that? Well, eigenvectors are an intrinsic Olive is, I'm sorry, I'm getting tripped up. My cat is rubbing her face on the computer while I'm trying to talk to you. You may or may not hear weird cat noises. But yeah, so, right, why would you care about the eigenvectors forming a basis, right? Well, eigenvectors are intrinsic entities to your matrix, right? They reveal information about how your matrix behaves, right? Multiplying a eigenvector by a just scales it. So, in the eyes of the matrix, those vectors are very important. And a matrix, in practice, you're going to be getting a matrix and it's going to be coming from data. And if your data has enough eigenvectors that form a basis, right? And we know if you have a basis, well, right, there's just a lot of linear algebra things you can do. So you can kind of see the need for a matrix needing to be diagonalizable, or at least hoping it would be, because that means you have enough eigenvectors that give you a basis, and with a basis, there's stuff you can do. So, surface value, you hopefully see why anybody would care about this. And the proof of this is actually quite slick, and the proof of this is quite nice because it actually furnishes a method for actually diagonalizing a matrix. So, in other words, given a matrix, if it's diagonalizable, it's similar, which means there's an invertible matrix P and a diagonal matrix D. The proof of this actually tells you how to create P and D, and we'll do that in a little bit. All right, let's actually do the proof of this. So suppose we're diagonalizable. We want to produce linearly independent eigenvectors. Specifically, I need enough of them to form a basis. Well, follow your nose. If I'm diagonalizable, just unravel the definition. I'm making the hand motion. So if you are diagonalizable, that means A is equal to P inverse dP, where D is diagonal and P is invertible. All right. Now what do I want? I want to produce n linearly independent eigenvectors. Well, the matrix D is diagonal, and maybe there's some zeros on it, so probably not invertible. But P is definitely invertible, and what do we know about invertible matrices? Well, one of the many equivalent things to being invertible is that your columns are linearly independent. And oh, hey, there happens to be n columns in the matrix P. Similarly for P inverse. So let's let V1 to Vn be the columns of P inverse. So in other words, P inverse, V sub k is equal to the kth column of P inverse, which another way of algebraically representing that is that it's P inverse times the kth standard basis element. So when we talked about matrix multiplication, we talked about, again, its connection between dot products of rows and columns, and how the columns of a matrix can get isolated via that matrix multiplication like this. Right, I wanted to remind us of this because we are about to use this characterization to great effect. All right, so what do I have now? Well, since P inverse is invertible, the columns must be linearly independent, so these V's are linearly independent. So the only thing I need to do is verify that they have to actually be eigenvectors. And now note, if you are diagonalizable, the entries in D are eigenvalues. So what I would need to prove now is that A times Vk is actually equal to dkk times Vk. Right, so that the eigenvalues on D correspond to these Vk. So let's just do that. Now, the real trick here is to note that when I announced diagonalization, I announced it as A is equal to P inverse times dP. That also communicated a bunch of information to you. It also tells you that P times A is D times P, and it also tells you that A times P inverse is P inverse times D. So there's kind of a, if you're thinking about matrix multiplication, multiplying A on the left of P inverse has the same effect as multiplying P inverse on the right by D. All right, and so now we just follow our nose with this expression in hand. If I look at A times Vk, my claim is that this is an eigenvector, so I want to prove that it's equal to a scalar multiple of Vk. And basically now just a bunch of magic happens, but we'll reveal the secrets. So A times Vk, the Vk, as we noted, is P inverse times the standard basis element Ek. A times P inverse, this portion right here, we know is equal to P inverse times D. Here I have a diagonal matrix multiplying something, and as we learned, a diagonal matrix multiplying something is just going to have the effect of keeping the columns, keeping the entry the same, and just scaling by the diagonal entries. And indeed, that is true. So multiplying D by the standard basis element Ek will just give us Ek scaled by the kth entry in the diagonal matrix. This here is a scalar, so I can pull it out. And, oh, looky here, P inverse Ek that is how we defined v sub k in the first place. And there we go. The v sub k's are indeed eigenvectors. And their associated eigenvalues are precisely the corresponding diagonal entries in D. Beautiful. So now we've seen that if you are diagonalizable, the breakdown of P inverse dP is, right, the D has to be the eigenvalues, and the P inverse matrix has to have the corresponding eigenvectors in its columns. So actually, we now know that if you can diagonalize, we know how to compute P inverse in D. Pretty cool. Right, but unfortunately, this is an if and only if, so let's take the time to do the other direction. Now, the other direction is not bad. It's a little bit more involved than the forward direction here, but the same idea is going to go down. If I have enough eigenvectors, well, the proof here just revealed that the P inverse matrix has to consist of the eigenvectors, and the D has to consist of the eigenvalues. So let's say we have linearly independent eigenvectors v1 to vn. For each vk, there is an eigenvalue associated with it. Now, again, it's worth noting that for each vk, the lambda k's are not necessarily distinct, right? It's possible that one eigenvalue produces multiple eigenvectors, right? So you can have an eigenvalue of 5, but you generated like 1, 0, 0, and 0, 1, 0, or something like that. Okay, but anyway, we can find one for each because they're eigenvectors, so there's an eigenvalue. And, oh, look, I've got a n real numbers, so I can make a diagonal matrix by putting those in the diagonal and 0 everywhere else. All right, so now we just need to create P. So to make our lives easier, we're going to use Q here, because we already saw that P inverse is what has to have the eigenvectors in it, so we're just going to start with Q. Let Q be the matrix whose columns are that. You might be asking, well, why don't you do P inverse? There's reasons, so we'll just leave it at that. Anyway, so we'll let Q be the matrix whose columns are v1 to vn. All right, note that by hypothesis, Q has to be invertible because these are linearly independent. And furthermore, they have to be eigenvectors. And why does that? And furthermore, A times Q has to equal Q times D. Now, why does that happen? Well, if you look at the kth column of A times Q, that is the same thing as multiplying the vector, the kth column of Q by the matrix A, because, again, it's just how matrix multiplication works. Dot product of this, of rows of this with columns of this, so it, if in effect, is the same thing as this. These are, the matrix Q is constructed so that its columns are the VKs. The VKs are eigenvectors, so this must be true. This is the kth entry of D. All right. VK is Q times the standard basis element EK. Then we sneak this in. That gives me D times EK, and multiplying a matrix by EK gives you its kth column. So the matrices AQ and QD have the same column, so they must be the same matrix. So AQ is equal to QD. Beautiful. All right. All right, and as I already let slip, since V1 to Vn are linearly independent, the matrix Q is invertible, so multiply both sides of this equation by Q inverse on the right. And then setting P equal to Q inverse then reveals that A is equal to P inverse dP, and thus A is diagonalizable. So note, the algebraic part right here, while contextually is a little different, we still made the same little trick of pulling a scalar in and rewriting this as a matrix multiplication. Neat little trick. So again, as we proved, multiplying by diagonal matrices, in effect, is just doing scaling on each row. And for the standard basis element, because everything's 0, that means you're just scaling 1, and so it pull a little sneaky on you. It's pretty cool. And yeah, there we go. So now we have proven that diagonalization happens precisely when you have enough eigenvectors to form a basis. So naturally, we want to know, well, when do you have enough eigenvectors to form a basis? Well, we know it's equivalent to being diagonalizable, but it'd be great if there was another thing we could use to prove that, so then we can get diagonalization is equivalent to something else. And it turns out that there is some conditions that are known that are out there. Obviously, the necessary and sufficient ones are that you're just diagonalizable, but there are some conditions to ensure there are enough eigenvectors. And probably the easiest one for us to prove today, and this will be the last thing we prove before we go through a nice little example, is that if you have enough eigenvalues, distinct eigenvalues, you must have enough distinct eigenvectors. So specifically, we'll prove that if we have an n by n matrix and m distinct eigenvalues, then the associated non-zero eigenvectors must be linearly independent. Okay. And again, obviously, non-zero is a requirement. I'm trying to prove something's linearly independent. The zero vector can't come along to the party. Alright, so this reveals here that distinct eigenvalues will produce linearly independent eigenvectors. Pretty cool. Now, that doesn't say that if you have an eigenvalue that produces multiple eigenvectors that they're necessarily linearly independent or not. But for us, this will give us the goods. All right. Now, the proof of this is going to be quite interesting because this is probably going to be maybe the first or second time you've seen a proof where we're going to not like exactly do induction, but it's an induction style proof. So because any non-zero vector itself is automatically linearly independent, and why do I have the word distinct there? Let me, as always, you go for the slides and you think it's good. Let me, hold on, let me fix that. Linearly independent. Every time, man, Alright, let's fix it. Okay. Alright, so, yeah, so when V1 is, since V1 is a non-zero vector, we know it's automatically linearly independent. So if you look at the set of integers from 1 to m, so that the vectors V1 to Vk are linearly independent, this is a non-empty set of positive integers. And note, it's automatically bounded above. So if I have a non-empty collection of a finite amount of integers, there's a biggest one somewhere in there. Right, so that fact you can demonstrate is equivalent to induction. So that's why I was saying it's kind of like an inductive style proof. So basically the idea is we set up a set of integers, we know it's not empty, and we know it's finite, so there is a biggest one, and then we'll prove the biggest one is what we want it to be. Specifically, we want it to be m, because then, well, that's what I want to prove. I want to prove all of them are linearly independent. So it's kind of induction where we're showing, well, if I start with 1, it's linearly independent, and now I'll show that, okay, I have to, if I start adding more and I lose linear independence, I have a contradiction. So it's not quite induction, but it's this technique is similar. All right, so let's suppose for contradiction that j is strictly less than m. So I have that v1 to vj are a linearly independent collection of set of vectors. However, once I get to j plus 1, I lose linear independence, and so those become linearly dependent. All right, I'm going to prove this cannot happen. All right, so since they are not linearly independent, there are scalars I can find that when I scale and add them up, I get to 0, and some of the scalars need to be non-zero. And this should remind you of something we pulled. We pulled a similar proof a long time ago where now we note, hey, by the way, if alpha j was actually equal to 0, then I have this expression, but the linear independence of the list I had forces all of the scalars to be 0. So it's got to be that the last one that we added is in fact non-zero, right? Because the list v1 to vj was linearly independent, and once we added something to ruin that linear independence, well, the non-zero scalar is going to have to come into play on the new thing I added, because the scalars work with the other things. Alright, which means then that, oh hey, I can write v sub j plus 1 as a linear combo of v1 to vj. Right, so and again, we kind of know this to be true. If you're linearly dependent, that means something is a linear combo of the others. Right, and here what we're kind of explicitly seeing is that if I know v1 to vj is linearly independent, but once I add vj plus 1, it's no longer linearly independent, well then vj plus 1 must be a linear combo of the others. So, just reminding yourselves of that fact and working out the details of that proof again. Alright, well, now what is going to happen? So, what do we know about beta 1 to beta j? Well, right now you might think I don't know anything. I don't know what's going on. And I agree. But we know something about beta 1 to beta j. We know something about them has to be true based on our hypothesis. Our hypothesis were that the V1 to VMs are all non-zero. So I know that beta 1, beta 2, all of the beta j, I know that they all cannot equal 0. Because if they all equaled 0, this would equal 0. And that's a problem. Okay. All right. And alpha k. It should be beta. This should be beta k is equal to that. That's what's going on there. So if he says this beta, that should be a beta k. Yeah, j is already fixed. K is our dummy variable. All right, cool. All right. Now, so we know that the betas have to all be non-zero. However, what else do we know about the v's? We know they are eigenvectors. So what happens when I multiply this by a? All right. All right, well, if I multiply v sub j plus 1 by a, well, v sub j plus 1 is a eigenvector, and specifically associated with the eigenvalue lambda j plus 1. V sub j plus 1 we know is a linear combo, and matrix multiplication distributes, and these are all eigenvectors, so they multiply out correctly like this, giving us this expression. So we've got that scaling v sub j plus 1 by alpha j plus 1 is equal to this linear combination of the v1 vj's. However, I already have a linear combo for v sub j. I already know it's equal to this. Right, so if I were to multiply it by alpha j plus 1, all right, I would just be multiplying it by alpha j plus 1 like this. Right, so note here, I picked up, when I multiplied by a, I got this, but we also know that, well, if I just scale it, it would equal this as well. So here, we multiplied by a and got this expression, and here, well, we just know this is equal to this, so I can just scale both sides by alpha j plus 1. And since those are both equal, we then subtract. We get 0 on the left, and on the right, well, the betas come for the ride, the v1s go for the ride, and then I get lambda 1 minus lambda sub j plus 1, all the way up to lambda j. And now we have this linear combo is equal to 0, but v1 to vj, by its construction, is linearly independent. So all of those scalars must equal 0. But what else did we assume about the eigenvalues? So remember, our hypotheses were that we had a matrix, we had distinct eigenvalues, and we had non-zero eigenvector associated eigenvectors. I haven't used the fact that the lambdas are different, but we know they have to be different. K here is running from 1 to j. So lambda k minus lambda j sub plus 1 must always be non-zero. The eigenvalues are different from each other. So a lambda j plus 1 is not equal to lambda 1, lambda 2, all the way up to lambda j. So, hey, this product is equal to 0, and I know part of it is always non-zero, so it's got to be that all the betas are 0. But since all the betas are 0, that means v sub j plus 1 must equal 0, going against our hypothesis that what I had were non-zero eigenvectors. Beautiful. And the proof is over. It's got to be that j was in fact m, right? If j was not equal to m, if there was a point in the list where we were linearly independent, but in the next element we failed, can't happen, because the only way that that could fail is if the vector was 0, but we just proved that's not allowed. Beauty. Neat little proof, gotta say. And again, a proof that lands in my favorite paradigm of all of my hypotheses are showing up, right? The format of this proof, though, like I said, is a little tricky. It's kind of this weird, like, maximum kind of argument. But again, all of the facts, the fact that we're eigenvectors, the fact that we have distinct eigenvalues, all of that stuff is, you know, coming into play and working the way you want it to. It's beautiful. All right. So, equipped with this, let's actually go through the process of diagonalizing a matrix, and that will call it for today. Okay, so let's actually wrap things up by actually going through diagonalizing a matrix. Here's a matrix. Negative 2, 3, 2, negative 1. Alright, well, let's compute the eigenvalues. Not too bad. Again, it's a 2 by 2, so we can immediately jump to the characteristic equation. 0 is equal to lambda squared minus the trace of the matrix, negative 2 plus negative 1 times lambda, plus the determinant of the matrix, negative 2 times negative 1 minus 3 times 2. That gives me lambda squared plus 3 lambda minus 4, which factors like thus. So we find that our 2 by 2 matrix has two distinct eigenvalues. And by the previous proposition, my two distinct eigenvalues must produce two linearly independent eigenvectors. So I know that this matrix has to be diagonalizable. It has enough eigenvalues to ensure there are distinct eigenvectors. Now again, that was an implication, right? If you have enough eigenvalues, you've got you have enough linearly independent eigenvectors. If you don't have enough eigenvalues, it doesn't immediately torpedo you, as we will see in practice problems. But if you do have enough eigenvalues, we know we've got enough eigenvectors, so if I want to diagonalize this matrix, I just need to find the eigenvectors and compute P inverse and compute P. So the eigenvectors for lambda equals 1, so subtract 1 off the diagonal. This matrix here is guaranteed to be not invertible, so that's a good check to make sure we didn't screw up any computations. Indeed, this matrix fails to be invertible for a variety of reasons, and from the equations here we see that V1 is equal to V2, both this dot product with that equaling 0 and this dot product with that equaling 0 give me that information, and so we know that the eigenspace is just any scalar multiple of the vector 1, 1, right? If V2 is equal to 1, then V1 has to equal 1, and there we go. Alright, now if I want to get the eigenspace for lambda equals negative 4, I do the same thing, subtract negative 4 off the diagonal, so add 4 to the diagonal. Alright, now here the expression that we get is 2 V1 is equal to negative 3 V2. Now, obviously, something you could do is let V2 equal 1, which would then give you that V1 has to be negative 3 halves, but especially in the diagonalization process, it is always in your best interest to just make sure everything is a nice integer, just to make your computational life easier. So instead of solving for this as we would normally do and get V is equal to, and get that the vectors are a scalar multiple of negative 3 halves 1, well, if you let V2 be equal to 2, the 2's cancel. That tells you that V1 is negative 3, so all of the eigenvectors have to be some scalar multiple of negative 3, too. Right? This is just sort of the integer one. Obviously, you can scale this by whatever you want, and you can use that as your representative as long as it's non-zero. But anyway, that's how I went about getting this eigenspace. And now, equipped with all of this, our matrix has to be diagonalizable, because, again, we know that since it has two eigenvalues, and it's a 2 by 2, it must have two linearly independent eigenvectors, so it's got enough to be diagonalizable. And in particular, we know from the proofs of the diagonalization being equivalent to having enough eigenvectors to form a basis, we know that the D has to be the eigenvalues placed accordingly, so 1, negative 4, and the matrix P inverse has to be the associated eigenvectors. So the first column here, 1, 1, has to be an eigenvector associated with 1, and the second column has to be an eigenvector associated with negative 4. Right? Again, we picked, integer representatives to make our lives easier, because to truly diagonalize a matrix, you need to tell me what P inverse is, you need to tell me what D is, and you need to tell me what P is. Well, to figure out P, I have P inverse. P is equal to P inverse inverse. So we just find the inverse of P inverse. So we compute the determinant, do 1 over it, swap the diagonal, negate the off diagonal. Ooh, minus sign missing right there. Boo! 2 out of 10, learned nothing. Alright. I only had to fix 2 mistakes. Let's see what the other one was, just some copy pasta nonsense. This was me just forgetting a minus sign like an idiot. Alright. Grade A stunado over here. Alright, but we pick up a 1 over 5, and as noted, there's kind of no promise that the inverse of a matrix is anything nice looking. Right, I mean, this could be worse. But anyway, equipped with this, we now know that our original matrix -2, 3, 2, -1 is indeed diagonalizable, and in fact, I can write it out as the product of three matrices here. So note, I actually factored my matrix into maybe pretty interesting things, right? I was able to take my matrix and factor it into its eigenvectors and its eigenvalues, and then just some, shit over here. I'm 30 minutes into the YouTube video. I can start fucking swearing now, without getting in trouble. You can't swear in like the first 5 minutes or something like that. I forgot. Anyway, there's so not that I monetize these or anything. I don't think I can yet. I don't know, subscribers. I don't know. Yeah, I don't know. I don't pay attention to my YouTube channel. But anyway, smash that like button. Subscribe to my farts. Alright, okay, I'm losing it. Alright, lost the thread. This is over. Okay. Bye!